Have you ever just stopped and wondered what holds everything together? I mean, from the water you drink to the air you breathe, all the way out to the distant stars. There's this invisible force at work, a kind of cosmic glue. Well, today we're going to dive into what that is, the incredible world of chemical bonding. So yeah, let's just put the big question right out there. What is this invisible glue that stops matter from just poof, flying apart? The answer, it turns out, is the chemical bond, and the whole thing is driven by one really simple, universal desire. And what is that desire? It's for stability. You know, it's kind of like us. Atoms are on this constant, relentless quest to find a calm, stable state. But for an atom, being stable really means one thing above all else, and that's energy. Okay, and this might be one of the most important roles in all of chemistry, so really let this sink in. Stability and energy are total opposites. The more you have of one, the less you have of the other. Think of it this way. When you're running a race, you're full of high energy, right? But you're not stable. But the moment you cross the finish line and collapse on the couch, your energy plummets, and boom, you are stable. Atoms work the exact same way. So, this whole process brings us to what a chemical bond actually is. It's simply an attractive force that pulls atoms together. And they do this so they can shed their excess, frantic energy and settle down into that comfortable, low-energy, stable state they've been searching for all along. And this is absolutely crucial because atoms are moving from that high-energy, unstable state down to a low-energy, stable one, forming a bond, always releases that leftover energy. It has to go somewhere. That burst of energy, maybe as heat or light, is the universe's sign that a stable connection has just been made. Okay, so we get it. Atoms want to be stable, and they do that by lowering their energy. But how do they know when they've hit that sweet spot? How do they know when they're done? Well, it turns out there's kind of a rule book for this, and it has a very specific goal in mind. You know, in the world of elements, there's a group of cool, aloof celebrities that all the other atoms want to be like, and those are the noble gases. They are the absolute epitome of stability. They don't need to react with anyone because they're already perfectly content, perfectly stable, all on their own. So what's their big secret? How are they so stable? Well, they all share one thing in common, a full outer shell with exactly 8 electrons. That's it. This magic number of 8 is the key to their perfect stability. And this leads us to the single most important guideline in bonding. It's called the octet rule. And it's simple. Atoms will give, take, or share electrons. They'll do whatever it takes to end up with a full outer shell of 8, just like their noble gas role models. Achieving that perfect octet is their ultimate goal. So, if getting to 8 is the name of the game, how do atoms actually do it? How do they pull it off? It turns out they have 2 main strategies for hitting that magic number. The first strategy is called ionic bonding, and it involves a complete transfer of electrons from one atom to another. The second is covalent bonding, which is much more of a partnership, a mutual sharing of electrons. So let's break down each one. First up, let's talk about the straightforward transaction of ionic bonding. This happens when you have a clear giver, an atom with an extra electron it's happy to get rid of, and a clear taker, an atom that desperately needs just one more to complete its octet. The classic example is just plain old table salt. You've got sodium with one lone electron it's eager to offload. Then there's chlorine, which has 7 outer electrons and just needs one more. So sodium literally gives its electron to chlorine, a full transfer. Sodium becomes positive, chlorine becomes negative, and bam, those opposite charges attract each other, locking them into a super strong ionic bond. And now, both atoms are stable and happy. But what happens when you have 2 atoms that both want to take an electron? You know, neither one is willing to give one up. In that case, they have to move on to strategy number 2. Cooperation through sharing. Let's take 2 chlorine atoms. Each one starts with 7 outer electrons, and each one needs just one more to be stable. So they make a deal. They each put 1 electron into a shared pool in the middle. This shared pair forms what we call a covalent bond. Now both atoms get to count those shared electrons as their own, and voila, both of them achieve a stable octet. It's a perfect win-win. So we've seen how atoms bond to become stable. Now let's tie this all back to where we started, energy. Because the amount of energy involved tells us just how strong and stable these new connections really are. We measure this with something called bond energy. It's defined as the amount of energy that gets released when a mole of these bonds is formed. But here's the cool part. It's a perfect mirror image. It's also the exact same amount of energy you'd have to put back in to break that very same bond apart. And this right here, this is the big takeaway. Think of that released energy as the price of stability. The more energy an atom pays by releasing it to form a bond, the deeper it sinks into that stable state and the stronger that connection becomes. A high bond energy means you've got a rock-solid bond. And that leaves us with one final thought to chew on. We've seen that making bonds releases energy and creates stability. So, what does that imply about the reverse? What does it take to break stable compounds apart and rearrange them into something new? Well, that process, that's the foundation of every single chemical reaction in the entire universe. Something to think about.